Okay, so I think I want to first finish the forecasting part that I do not quite finish last class, and then I will talk more examples of the estimation and the forecasting. Okay, so in last class we say that if our model is a AR1 model, so xt is equal to phi xt minus 1 plus wt. Okay. Then the one step ahead forecast is phi xt. Let's use xn. Yeah, so suppose our model is the AR1 model, and we have data from the first period to period number n, so all the way x1 to all the way to xn. And then the one step ahead forecast we showed in last class is equal to phi xn. Okay. And the mean squared prediction error. So the mean square prediction error is the expectation of your true observation of xn minus 1 minus your forecast error, so which is xn minus 1 given all the data n. So this would equal to e xn minus 1 phi xn minus 1. Sorry, not xn. Okay. And by our AR model, this just equal to wn. I'm sorry, I think this is not. So we are doing square. So here is, sorry, so. Oh, yeah. I think this is correct. This is the square error. Okay. Okay. And by definition, because we are considering AR1 model, the expectation of Wn plus 1 square is just equal to the variance of the white noise W. Okay, so the mean squared prediction error measures like how good your prediction is. Okay, so it captures that the deviation of your prediction value, okay, in expectation. Okay, and we show the two-step ahead forecast is phi square xn xn. Yes. And if for the two-step ahead forecast, the mean squared prediction error is equal to the true value of two-step ahead minus the forecast. And this would equal to We also show the m step is equal to phi to the power m xn, and its corresponding MSPE is this would equal to right. So let's look at this m step ahead forecast more closely. Okay. So for this m step ahead forecast, the forecast xn plus m given n is phi to the m xn, right? And we say we can see if m goes to infinity, okay? And since our AR model is a causal and invertible model, so phi is less than, the absolute value of phi is less than 1, okay? So if this is the case, then xn plus m given n would go to 0. Yeah. So which is there? So what is 0? So so 0 here is the mean of the data. Okay. So why? So because look at our model. This is 0. So we have like the expectation of xt is equal to phi of the expectation of xt minus 1. And because our model is a stationary model, so this implies that the expectation of xt is equal to 0. Okay. So the m step ahead forecast just simply tell us that it is 0. It is the mean of the data. So that means it is not that informative if you want to do m step ahead forecast and this m goes to infinity. It's actually not that informative. Okay, yeah, so I think that's also a restriction of our like ARMA model. Okay. Yeah, but if you only want to do like one step or 2 steps ahead forecast, I think that would be still might be still a good model to do the forecast. But if you want to do a infinite step ahead forecast, then it might not be a good choice. Okay. Yeah. And moreover, yeah, this is not. You can show by using like the geometric series summation rule, you can show that the MSPE would go to sigma W sigma square over 1 minus phi square. Okay, so this is the variance of xt. Yeah, so if you check the autocovariance function of the xt, and you can show that this is exactly what it is. Okay, so it is the variance of the xt. This is important. So if you use this AR1 model to do a infinite step ahead forecast, then your forecast should go to the mean of your data. Yeah, and also suppose if your model is a AR1 with a drift. Okay. This is AR1 with a drift. Let's write in this way. So if your model has a drift, then the forecast would include that drift as well. Okay. So the xn plus 1 given n is mu plus phi times xn, and the m step ahead forecast is mu plus phi to the power m times xn. Okay, so that's the AR1 model forecast. And we can actually extend this result to, or this idea to our ARMA model. Right, so to do the ARMA model forecast, like the closed form solution, it's not that easy. It's not as simple as the AR1 forecast. So we usually ask the computer to do those forecasts for us. Yeah, but I mean, I might still talk a little bit like theory of the ARMA forecast here. Yeah, so it's a slightly different as the AR1 model. So this general case is slightly different, or I mean, slightly complicated than the AR1 model. Okay, so because our ARMA model is causal and invertible, so that means we can write it as a AR infinity representation. Okay, so that is WT is equal to XT plus J equal to 1 pi J XT minus J, right? Yeah, XT minus J. Okay. Right, and we can reorder terms. This is XT equal to negative J equal to 1 pi J XT minus J plus WT. Okay. Then we can do sort of like the forecasting. So xn plus m now is equal to from 1 pi J xn. Yeah, so all I do here is that I replace t by n plus m because we want to do some forecast. Okay. Okay. So if we have infinite amount of data, okay, so we have the data from x1 all the way to xn. No, sorry, let's write it in this way: xn minus 1 all the way to x0, x1, x -1, all the way to x infinity. Okay, so if we have like infinite amount of data, okay, then our prediction or our forecasting is actually easy. Then xn plus mn is that you can just plug in everything here. Yeah, so you can see even though this j goes to infinity, but since we have infinite amount of data, then this forecasting is actually a valid forecasting. Okay, yeah, but this would require that we have infinite amount of data. However, in practice, we can never have an infinite amount of data. We can never have a data all the way to negative infinity. Okay, so in this case, we will do some like truncation stuff. Okay. So instead of from j from 1 to infinity, we will have j from 1 to n plus m minus 1. Okay, so that's all the data we have. Okay. Let's maybe we only have data x1 to xn. This we can only starting from period number 1. We do not have like periods negative in negative infinity. Actually, we do not have data x minus 1 or x minus 2. Okay, so I mean in practice, what we do, or actually what the computer does, is that it truncates the data from x0 to x negative infinity, and only use the available data to do the forecasting. Yeah, so that's actually what the computer does. Right, and by using this formula, you can also show the mean square error, mean square prediction error. Yeah, so it's also a function of your white noise variance. Okay, the white noise variance times some like the weight of like your AR representation. Okay, so I think that's not important, but I just want to say that this is actually what the computer does. Okay, so it only uses like the finite amount of data to do the forecast. Okay, yeah, but the things that if you can notice that if like you have a very long time series, and this pi j, which is like the coefficient of this AR representation, would converge to 0 when j goes to infinity. So that means like if you have a long series of data, then the early values of this time series would have very little effect on your future prediction. Okay, so that's why I think this forecast works, and I think it works in the asymptotic part. I mean, in the asymptotic theory. Okay, so this, yeah, so what we get rid of is would have very small effect on our forecast. So we can like in what sense we can in some like mathematical sense we can just ignore that part. Okay. And to make this also as a valid forecast. Okay, so that's all I want to talk about for the forecast. So any questions? Okay, so if there's no question, I think I want to do more R examples. Okay, so so the example that I did last class is this MA1 model of the diff log of the WRF. Okay, so that's what we saw in last class. Okay, and we find that so this is a MA without constant on diff log WRF. Okay, and we want to check a bunch of things. So first, that we want to check whether the MA coefficient is significant, and this is that you can check from here, right? So it is significant, so which is good. Okay, and we can check whether this is a causal or an invertible model, and we find the coefficient of the MA1 is negative 0.77, so which the absolute value is less than 1. So that means this is a causal and invertible model. Okay. And the next thing that we want to check is the residual plot. Okay, so yeah, I think I will, after talking about this, I will spend some time talking about the residual plot. Okay, so this S-arima function or this S-arima command gives us, automatically provides us a lot of like the residual plots. So the first is the standardized residuals. Okay, so for this plot, we want it to more like to be a white noise. Okay, so we want this to have a constant mean, and we want this to have a constant variance. Okay, and we can check here that this graph actually shows us a constant mean and a constant variance, so which is pretty good. So this standard residual plot pass the check. Okay, and it would also give us the ACF of the residuals. So since that the ACF, the residuals, that what we want is that we want like everything within this confidence intervals, because we want the residuals to be a white noise. So that means the ACF gonna be equal to 0. Right? So but from this plot we can see overall the ACF plot is good, but this lag 1 is not that perfect. Okay, so it is a little bit large. Okay. Yeah, but overall it is fine. Okay, I think. And the third graph that this command gave us is this normal QQ plot. Okay, so this normal QQ plot, as I explained last time, so this blue line, yeah, I don't know if you can see it, but there's a blue line here. So this blue line shows you the normal distribution of the residuals, or the expected normal distribution of the residuals. Okay, and those dotted lines are the real observations. Okay, so if those real observations overlap with this blue line, then we see that our residuals follow a normal distribution, and which is something that we want, but it is not required. Okay, it is not required, but it is something we want, even if like your residuals does not follow a normal distribution. That's fine, because we do not have assumptions that our residuals need to be a normal distribution. Okay, we only want it to be a white noise, but I mean the normal distribution is a very important case of the white noise. So I mean, in most cases, people want the residuals to follow a normal distribution. And you can see from this graph that this is not bad. Okay, so we have some outliers, or we have some data points that do not follow exactly this blue line, but the lucky thing is that they are still within the confidence interval. Okay, so this shaded region here, and actually there's the confidence interval also exists here, but you cannot see it very clearly because it's it's just in the same region as this blue line and this raw data. Okay, but you can see like this shaded region on the two ends of this normal QQ plot, and we see that our like those outliers are still within the confidence in this normal QQ plot, so which is not bad. Okay, and yeah, today I think I want to talk a little bit about like this LB statistic. Okay, so the general rule of this, so the general rule of this LB statistic is that we use this LB statistic to test our model is a good model or a bad model. Okay, and you can show that this LB statistic follows a chi-square distribution. Yeah, and the general rule is that if like all these p-values, so these are the p-values, so these are the p-values for the legs. Okay, so if the p-values are all larger than, or higher than this blue line, so this blue line is 0.05. Okay, so which is a cutoff point or cutoff line for the hypothesis testing. So if all these dots are larger than this blue line, then we think our model is a good model. Okay, so we do not reject the null hypothesis, and our null hypothesis is that our model is a good model. Okay, but you can see here is that all the points are actually lower than this blue line. Okay, so this suggests that our model might not be a good model. Okay.
But I'm sorry, do you want them above or below?
I want them above. Okay. So let me have a new. So all the p-values, no, let me see. The p-values of all the legs yeah, I think I will put this together. Yeah, so I think later I will give you a guideline of like doing all this. So what you want to include. Okay. Okay. So this part I check the coefficients. I check it is significant or not significant. I check it is causal or check it is invertible. And this check the residuals. Okay. And finally, we can record the AIC and the BIC for our future use. Okay, so the AIC of this model is here. So it's 1.39399. Okay, and BIC is 1.413. Okay. Okay. So that's our first model, our MA1 model on this diff log varf. Okay, so we take the log in order to take care of the heteroscedasticity, and we take the diff in order to take care of the trend. Okay. All right, and we do not include the constant in this model. I think, yeah, we do not include the constant in this model. The reason is that we already take the diff. Okay, so the model is somewhat like demint. Okay, yeah, but of course you can include. You can like do no constant equal to f. Okay, and that would run a model that with constant. Okay, yeah, but not surprisingly, you can see that the mean, so which is this x mean, is almost equal to 0. Okay, because we do this difference, so there's like the mean should be equal to 0, and it is also insignificant. Yeah, yeah, and you can see that the residual plots are pretty much similar. Okay. Yeah, but we see that there are some issues with this model, right? Especially like this LB statistic and a little bit of like this ACF residual plots. Okay, so how about we just include more terms in this model? Okay, so I consider a ARMA 1-1 model. Okay, so this is ARMA 1-1 without constant on this. So your change is that you change this P, which is order of ARMA of AR to 1, and the order of this MA equal to 1 as well. So that gives you the ARMA 1-1 model. Okay. And we do not include the constant in this model, but for sure you can. And if you include the constant gonna be equal to 0 because we already take the difference. Okay, so let's run this model and see what we got. Okay, so a couple of things. So we first say that the coefficients, so both coefficients are significant. So you can say both coefficients are significant, both AR and MA. Okay. Okay, so the next step is to check if there is any parameter redundancy. Okay, so the example that I gave in early class is that the AR-MA11 model might just only be a white noise model, right? Because if you like do those like cancellation, you will see that the AR-MA might just be a white noise model. Okay, so what we do is that we will check this parameter redundancy. Yeah, so as the email that I sent last night, so to check the parameter redundancy, you can of course check it by hand. You can just check it. And a easy way to do this in R is to check the root of the polynomials of the AR part and the MA part. Okay? So if the root of the AR part and the MA part are very similar, then we will think that there exists a parameter redundancy problem. Okay? So let's check what we have here. Okay, so we find that the root of the AR is about 4.3, and the root of the MA is about 1.12. Okay, so there's no parameter redundancy problem because the root of AR and the root of MA are different. Okay, so that's our check number 1. Check number 2. Okay, so check the parameter redundancy. Yeah, but I mean, in many applications and also in the textbook applications, they do not like do all this step. Yeah, but I think all of them are very important. Yeah. Yeah, but I mean, many applications or many authors do not do this very carefully or very clearly. But anyway, so in our class, I want you to do all of this, and I think it's a very good thing to present. Okay, and the third thing that we want to check is the causal and invertible. Right, so invertible. Yeah, so again, like in our in my last email, in my email last night, so I realized that the polyroot code in this package, in this ASTSA package, is different from what I taught in class. Okay, so if you find the polyroots, like in this code, if you put like the AR part in it and the MA part in it, and if you find the root is larger than 1, then that is causal and invertible. Okay, but what I taught in class is that
if the root of the polynomials are less than 1, then we have a causal and invertible model. Okay, so yeah, so the ideas behind both procedures are exactly the same, but they just have different ways to set up the polynomials so that you will have different results. And I think, as I said, so in order not to like confuse you, so we will not use like this polyroot command in R to check the causality and the invertibility of the model. Okay, yeah. So yeah, but for sure you can definitely use, but in that case you will check if the roots are larger than 1, not to check the roots are smaller than 1. Okay. Okay, so in our class, we will just use this ARMA to MA and ARMA to AR command to check the causality and the invertibility of the model. So we know that if we can, so we know that any causal and invertible model can be written as a MA infinity term and AR infinity representation. And the coefficient of the MA representation and the AR representation would converge to 0. Okay, so that's what we are looking for. And let's check this. So let's check the AR to ARMA to MA to check the MA representation. And you can easily see that the coefficients converge to 0. Okay, so it becomes smaller. Okay. And similarly, you can find that the ARMA to the AR representation, the coefficients also goes to 0. Okay. So the coefficients of AR infinity and MA infinity converge to 0. So the model is causal and invertible. Okay, so that's our check number 3. So now this, yeah, right. So yeah. So right now we have a pretty good coefficients check. So we find the coefficient significant. We do not find any parameter redundancy problem, and we find the model is causal and invertible. Okay. So then the check is the residual plot check. Okay. So the residual plot check. Okay. So let's check the first graph. So you can see this standardized residual plots are not bad. So the mean is approximately equal to 0. Very easy to see. And we do not have that much heteroscedasticity problem here. So the variance somewhat follows a white noise process. Okay. So the standardized residue, good. Okay. Then let's check the ACF plot. So you can easily see this ACF plot is much better than our previous ACF plot, okay? Especially this lag one, okay? So we do not, actually here we do not find any lags that have the ACF larger than the confidence interval. So which suggests that all the ACF are insignificantly different from 0. So very good. Okay, so the ACF plot, good. Another check. Yeah, and the normal plot, similar to what we have in early model. We still have some outliers here, but the lucky thing is that most of them are within the confidence interval. Okay, so good normal residues. Yeah, but again, as I mentioned, so this normal stuff is not necessary, but many people like it because they like to assume that the white noise follow normal distribution, but that's not exactly, I mean, that's not necessary. We can have like, we can allow like the error term to follow other distributions. Okay. Yeah, but anyway, here we have a not bad normal QQ plot. Okay, and finally, let's check this LB statistic. So you can see all the lags of the LB statistics, the p-values of all the lags are greater than 0.05. Okay, so which suggests that our model is a good model. We do not reject the null hypothesis. Our model is a good model. Okay, so that is copy this. Larger. Okay. And finally, let's compare the AIC and the BIC. Okay. So the AIC of this model is 1.37, and the BIC of this model is 1.39, right? So both are smaller than our first model, right? And we know that the smaller the AIC is, the better the model is. So they suggest that our second model is better than the first model in respect to with respect to AIC and BICs. Okay, better than MA1. Okay, so in conclusion, in conclusion, the AR-MA11 model is better than MA1 model. Okay, so we do all this analysis. We start from the coefficients we choose, and finally we check the AIC and the BIC, and we decide that the ARMA11 is better than MA1. Okay, yeah, but the rest of the question is that is this ARMA11 model the best model? Right, so is that true or not true? So in order to answer that question, you have to do more model selection analysis. Okay, so you perhaps want to include your AR order to 2, or you include your MA models to you increase your MA models to 2 and see like what that model looks like. Okay, and so you will do like more model selection, and finally you will decide which is your best model. Yeah, but here what I illustrate here is that the AR-MA11 is better than MA1. Okay. Right, and also later we will introduce the seasonality. So you perhaps also want to include the seasonality in your model and see if your model, if like the seasonal model is better than this non-seasonal model. Okay. Yeah, and also you can see that here we take the difference, and that's basically the integrated model, which we will talk next. So which is the ARIMA model. So this ARMA11 on diff log varf is basically the ARIMA 111 on log varf. So we will discuss that later. So we actually already like covered the ARIMA model. Yeah. Yeah. Okay. So I think that's, let me see. I think that's yeah. I think that's all I want to cover for this part. So I want to switch to the whiteboard and give you a short summary of what we learned and the steps of doing this analysis. Oh yeah, finally, and yeah, I forgot this, sorry. Let me do the forecasting. So yeah, I'm sorry about that. So I forgot the forecasting. Yeah, so this example is the forecasting. So we start with as ARIMA on a AR2 model, and yeah, this is what we got, and you can do the same analysis and check. Okay, yeah, let me quickly check. So this is ARIMA on the recruitment series with AR2 model, and you can see standard residual plots, not bad. ACF plots, not that good. We have a couple of lag have like larger ACF, and the normal QQ plots not good. You can see like those dots are outside your confidence interval. The LB statistics not bad. It's acceptable. Okay, so yeah, so you will do all this, and you will check like whether this is a causal and a invertible model. Yeah, but these coefficients are significant. You can just directly read from the results. Okay, so that's the ARIMA recruitment, and to do the forecasting. So as I said, this is what we do. So forecasting. This is what we do is 24-step ahead forecast. Okay, so this is 24 ahead forecast. So what we have here is that all these black dots are the observed data, and this red dots are the forecast data, and we do 24 forecasts. Okay, and these shaded regions are the confidence intervals. Okay, right. So you will notice that the forecast converges to mean. Okay, you can see that the forecast converge to this line, which is the mean. So I check the mean here. So the mean of this recruitment series is about 62. So you can see that it converges to the mean, which is 62. So this is exactly the same as the theory suggests. So as you increase the number of forecast steps, the forecast will converge to the mean. Okay, so sorry, 62.3. Okay, and the variance, I mean, the variance of the forecast converges to the variance of the data. Okay. Yeah, so, and again, this is also what the theory suggests. So you can see that the confidence band becomes pretty consistent once, I mean, the forecast goes to maybe after 12 or after 3, the variance becomes pretty consistent. And this is also exactly the same as our theory suggests. Our theory suggests that the variance of the forecast will converge to the variance of the data. Okay, and the forecast will converge to the mean. Okay. Okay, so that's the forecast. Yeah, so after after each model's estimation, the next step you want to do perhaps is to do this forecast. Okay, so let me switch to the whiteboard and give you a short summary. Let's just do ARMA here. So the steps to fit ARMA model. Okay. Yeah, so we have discussed like those steps already, but since we are talking more complicated models, so we will have like more stuff to add in our like steps. Okay. So step number 1 is to do the exploratory data analysis. Okay. We'll check if there's any trend. So if there's a trend, we will take the difference. Okay. And we will check if there is any heteroscedasticity in the model. Heteroscedasticity. And if there is, we will take the log. Okay. Okay. Yeah, and later we will check if there's seasonality, but we haven't gone to that yet, so we will postpone that part. Okay. So seasonality, not yet. Okay. Yeah. So in this class, yeah, there are more complicated like ARMA. I mean, there's more complicated time series models. We will do a little bit like the threshold regression, something like that. So all those stuff would come from the exploratory data analysis. So the exploratory data analysis would help you to determine which model you want to use. Okay, and for now we will focus on the difference of the trend to take care of the trend, and to use the log to take care of the heteroscedasticity. Okay, so that's step number 1, which is the exploratory data analysis. And step number 2 is to identify the dependence of the model.
basically is to choose P and Q of the ARMA model. Okay. And we use what? We use ACF and PACF plots to do that. Right. So if the ACF plot cuts off at leg number Q, then it's MA model, right? MAQ model. If PACF cuts at order number P, then it's ARP model. Okay, so we use the ACF and the PACF to decide our candidates of P and Q. So you might have a bunch of candidates, and the next step is that you will fit all these candidates and choose the best model. Okay. And number 3 is that you, as I say, you will use like these candidates to estimate the parameter. So it's the parameter estimation. So in our class, the command we use is that's the sArima command. Okay. Okay. And the 4th step is the diagnostics. Yeah, and there are a couple of things here. Okay. Number 1, coefficient significance. Yeah, so you can directly read the significance of your coefficients from the regression results. Okay. Number 2, let's see. Okay. So we want to check, we want to use the simplest model for our analysis. Okay. Or the parsimonious condition. Okay, so the parameter redundancy, and we use polyroot command in R to check the parameter redundancy. Okay. And number 3 is to check the causality and the invertibility of the model. Okay. And we use ARMA to AR, ARMA to MA to do all these checks. Okay. So if the coefficients converge to 0 in both of this like conversion, then our model is causal and invertible. However, if the coefficients do not converge, then our model is not causal and not invertible. Okay. Yeah, this might suggest that you might change to another model. Okay. All right. Yeah, let me call this diagnostics and model selection. So I think these two, even though some people like to put it separately, but I think they are very related. Okay, so all this like coefficient significance, all those diagnostic steps are important for your model selection. Yeah, so let's put it together. Okay, and number 4, you want to check. So let me have another page. Residual. Yeah, so I think I will give the, yeah, so you pretty much know what we want. Yeah. The residual. Okay. So the sArima gives residual plots. Yeah, so if I have time, I want maybe talk a little bit about like the series of those residual plots. But I mean, for now, let's just, I think you know like how to practically look at those residual plots and decide whether the residual plots are good or not. Okay, so to check the residues. And number 5 is that we want to check the AIC, BIC, and maybe it's, I don't know, some other information criteria. So I think the model, the R code also gives you this AICC, the corrected AIC. Yeah, so you want to check all this information criteria, and again, the smaller those information criteria is, the better the model is. Okay, yeah. So what you do is that you will do all this diagnostic and model selection steps for each of your candidates. Okay, and based on this, you will so based on the choose your best model. Yeah. And once you have your best model, and the final thing sometimes that we are interested in is the forecast. Okay. And the commands that we use is sArima 4. So here, clear, use the best model to do forecasts. Okay, so that's, I think, are the basic steps to fit an ARIMA model. Okay, and we discussed, yeah, I think, yeah, for now we have discussed why this is true. So we discussed the theories behind all these steps, and we discussed how we can implement all these steps in R. So I think the next thing is for you to use all this in your final project. So that means is that I want to see like all these steps in your final project. Yeah, so this seems easy, but it is actually not. Okay, so you will do a lot of model selection, and you might not find a best model. Okay, and in that case, yeah, you will either include more features in your model, or you will go back to your data sets. You go back to your to the content of your data and see why this is the case. Okay. Yeah, so these are just the basic steps. Yeah, so anyway, so let me know if you have any questions about your final project. Okay, so any questions? Okay, so if there's no questions, I think I will do a quick quiz to finish the ARMA model and also today's class. Okay, so let me switch. So that's question number 1.
let's have another minute, 1 more minute. Okay, I think I got all the answers. Okay, so yeah, so the correct answer are gonna be not enough information. The reason is that the PACF2 is the correlation between xt and xt minus 2 condition on xt minus 1. Okay, but in this regression model, we not only condition on xt minus 1, we also condition on xt minus 3. So the coefficient in front of xt minus 2 is not the coefficient. I mean, it's not the partial correlation between xt and xt minus 2. Okay, so in order to get the correlation between xt and xt minus 2, you just run the regression of xt, xt minus 1, and xt minus 2, but no xt minus 3. Okay. Yeah, so we do not have enough information to solve the PACF2. Okay. Okay, so that's question number 1, and let's see question number 2. Okay, I think I got everyone's answer. Yeah, so the correct answer is AR2. I think most of you got it. So to do this, you just check the ACF and the PACF table and decide if it's an AR model or a MA model. or maybe ARMA model. Okay, so if you do not get it, just check the table. Okay, so I think, yeah, including this quiz, that I think that's everything that I want to talk for the ARMA section. And yeah, and also I think, yeah, so I mean, as opposed to, it's late. Okay, yeah, so, yeah, so, yeah, so, and I think everything including today's class, so everything after midterm 1 and to today's class, and also including today's class, will be the materials for midterm 2. So which is 1 week from today. Yeah, so it's next Wednesday. Yeah, so the format should be pretty much similar to the last exam. So yeah, so all the questions are short answer questions. Yeah, so we will focus on the ARMA model for this exam, and also I want you to log in early. And after your exam, you can just take pictures and upload it to Moodle. Yeah, so the logistics are pretty much similar. And also you can bring a two-sided cheat sheet. I think that's fine. Yeah, so any questions about midterm 2? Okay, so yeah, so I will send you an email about the details of midterm 2, and if there are no questions, I think that's it for today's class. I will stop here, and next class we will move to the ARIMA model. Okay, so see you on Monday.
Thank you.